The muscle tutorial discussed the hill-type muscle model, what its parameters are, and how to use them to produce muscle contractions using a neural network. Just as it's important for animals to be able to use muscles to move, it's also important for them to get sensory feedback on how they're moving, so they can tell if the movements that they're attempting to make was completed successfully, and to know where their limbs are located. If you don't have any idea where your limbs are located in space, then there's no way for you to generate a motor plan to move your arm to reach for a food source or to strike a predator. Proprioceptors provide this type of sensory feedback information. Stretch receptors are dynamic sensors that allow an organism to detect the length and velocity of change in the muscle. It can use this to compare predicted movements to what's actually happening to detect errors. These sensors are dynamic in the sense that the nervous system can adjust them to cancel the predicted movements. Stretch receptors are fibers that are interspersed in with normal muscle fiber, but since there are so few of them, they produce very little tension. This means that when the muscle's length changes, the overall length of the stretch receptor will change by the same amount. Two types of signals come from these receptors. Type 1A fiber signals send back information on the velocity of the muscle, and Type 2 fiber signals send back information on the length of the muscle. Stretch receptors are also simulated using a hill-type model in AnimatLab. The model is shown here. In fact, this is really the exact same model that was used for regular extrafusal muscle fiber. The real difference between these two models is that the stretch receptor provides new sensory signals that relate the length of the SC and PE portion of the muscle to the Type 1A and Type 2 sensory signals. Stretch receptors are split into two sections, a nuclear bag region and a pole region. The nuclear bag region does not contract, while the pole region can. When the pole region is made to contract, this changes the sensitivity of the receptor to changes in length. The bag region is where the Type 1A signal originates that measures changes in the velocity of the muscle, while the pole region is where the Type 2 signal originates that measures length changes. The model assumes that the lengths of the SC and PE sections of the simulated muscle are linearly proportional to the firing rates of the Type 1A and Type 2 fibers. The user can specify constants that convert these lengths into firing rates. Let's begin this tutorial by loading the muscle project. This project is located at C, Program Files, AnimatLab, Tutorials, Body Parts, Muscle. Once the project is loaded, select the Save Project As item from the File menu and change the name to Stretch Receptor. The first thing we need to do is disable the muscle from the previous tutorial. The muscle tutorial uses a virtual test rig that allowed us to manually change the length of a muscle at specific velocities. We'll be using that functionality again to stretch our receptor by 1 centimeter at different speeds to see what effect it has on the firing rate of these two fiber types. Set the default body part type to be linear hill stretch receptor and add it to the arm. Change its name to be stretch. Set the KSE spring constant to 35 newtons per meter, KPE spring constant to 5 newtons per meter, the damping coefficient B to 10 newton seconds per meter. To learn more about these parameters, please review the tutorial on the muscle model. Next, string the receptor by adding the attachment points. Set its L width parameter to be 10 centimeters. Next, we need to set the firing rate constants. These constants are multiplied by either the SE or PE segment length of the muscle to determine the actual firing rate. So when you're designing your own receptors, you need to keep in mind that the final firing rate of the muscles will depend on the muscle lengths. So for two muscles with different lengths to have similar firing rates, you'll need to adjust these firing rate constants appropriately. Let's set the 1A firing rate constant to be 1100 spikes per second meter, and the Type 2 firing rate constant to be 360 spikes per second meter. As I mentioned earlier, stretch receptors are interspersed in between regular extrafusal muscle fibers, and there are only a handful of these fibers compared to regular ones that produce force to move the limbs. This means that stretch receptors produce very little force on their own. The model in AnimatLab has a flag called Apply Tension. This flag is false by default. This means that any tension that's generated by the receptor is treated as an internal signal that helps the receptor calculate muscle length changes. but it doesn't apply this tension to the body parts. If you do want the receptor to apply tensions, then you should change this flag to be true. Now let's close the old chart and add a new one to view the receptor length and type 1A and 2 fiber firing rates. Set the end time to be 5 seconds. We'll be stretching the receptor by 1 centimeter over a range of speeds from 2 centimeters per second to 0.5 centimeters per second. Let's begin by selecting the stretch stimulus and setting its end time to 2.5 seconds, start time to 2 seconds, and velocity to -2 centimeters per second. Now disable the relaxed stimulus. Run the simulation. Notice that the type 1A fiber signal has a sharp peak that rises rapidly during the stretch when the velocity is high, and then it decays back down to a new steady firing rate, whereas the type 2 fiber moves steadily from one firing rate to a new rate. Export this data and rename the exported file as a.text. Change the stretch stimulus. Set its end time to 3 seconds and its velocity to -1 centimeter per second. Again, export the data and change the file to be named b.text. Change the stretch stimulus again by setting its end time to 4 seconds and its velocity to -0.5 centimeters per second. Export the data again, naming it c.text. Now, import the 3 data files into Excel and produce charts to show the length and type 1A and 2 firing rates for all 3 velocities. When you do this, you'll obtain charts that look like these. Notice how as the velocity is decreased, the response of the type 1A fiber is also decreased. So the faster the receptor is stretched, the greater its response. This shows that it's strongly affected by the velocity of the muscle. In contrast, the type 2 firing rates move tonically from one steady firing rate to another without any peaks like the 1A fiber. This signal provides a good estimation of the actual length of the muscle. Now let's go back and relax this receptor after it's been stretched and see what happens. Set the stretch stimulus endpoint back to 2.5 seconds and its velocity to -2 centimeters per second. Set the relaxed stimulus endpoint to 5.5 seconds, start time to 5 seconds, and velocity to 2 centimeters per second. Then enable it. Now change the chart end time to 7 seconds so we can see the receptor relax. When the receptor relaxes, the 1A firing rate drops like a rock and hits a floor where the firing rate doesn't go any lower. So why did this happen? The problem is that once the tension in the receptor is dropped to 0, the SE segment of the muscle can no longer decrease its length, so it will have reached a floor where the firing rate can no longer decrease. The PE segment, though, does still decrease. This is because it's decreasing in order to ensure that the length of the two segments is the same as the overall length of the muscle. So, does this mean that we can only use this spindle to detect stretches, but not relaxations of the muscle? Not at all. What we need to do is to cause a small contraction in the receptor. This stretches the SC portion and allows it to be sensitive to both stretches and relaxations. Go back to the behavioral editor and add a new stretch receptor node. Set its name to be stretch. Now add a new non-spiking neuron. Change its name to SV for stretch voltage. Set its resting potential to -100 millivolts and its time constant to 100 milliseconds. Now connect SV to the receptor node. Leave the adapter settings as the default. Next, we need to add a stimulus that would cause the receptor to apply 1 Newton of tension if it was configured to apply forces. Go to the Calculate Stimulus property of the receptor. Change the tension value to 1 and hit Calculate. We need a voltage of -52.16 millivolts. The non-spiking neuron has a default conductance of 1 microsiemens, and its resting potential is -100 millivolts. So we need a current of 47.84 nanoamps to produce the desired voltage. Add a tonic current stimulus that runs for 20 seconds using the current value. Now run the simulation. Nothing happened. So what went wrong here? This demonstrates an important point for when you're trying to connect parts of the body to the neural network. Each of the node items must be told which part in the body they correspond to, so they'll know which receptor or muscle to apply their inputs towards. If you forget to do this, then even though we're stimulating the neuron and changing its membrane voltage, this signal will not be propagated to the receptor and it will not produce any effects. Select the stretch receptor node and set its spindle ID to be stretch. Now let's try and run the simulation again. This time the firing rates of both the type 1A and 2 fibers go up to a new level. When it's stretched, we get the same type of responses we saw before, but now when it's relaxed, we're also able to detect decreases in the 1A firing rate that reflects this. We can get a better view of the changes if we set the 1A axis to range between 75 and 95 spikes per second. And the type 2 axis to range from 150 to 160 spikes per second. This tutorial has discussed the model used to simulate stretch receptors and muscle spindles within AnimatLab. It's also shown you the difference between type 1A and type 2 fibers and the types of information that they convey. The nervous system can contract these receptors to change their sensitivity, and this allows your body to use the type 1A signal as an error detector when comparing predicted movements to actual movements. To learn more about this subject, please see the stretch reflex tutorial in the examples section.